In 3.1 E, F, and G, we're going to talk about the basic properties of correlation. You actually did in some applets related to calculating and interpreting correlation, and then explaining how the correlation, which is the letter R, is influenced by extreme observations. So first, let me show you the formula for correlation. Correlation, one thing to highlight, is only for linear patterns or for lines. And it is defined by the letter R. So an R number is not calculated, example, for a parabola or an exponential function, only for linear patterns. This formula here is found on the AP exam in their formula sheet if you need to use it. In this case, what they're going to do is on the outside, it's 1 divided by n, which is your sample size, minus 1. So if you have a sample size of 20, this will be 1 over 19. What you're going to do is you're going to sum. If the sample size is 20, you're going to do 20 elements, and you're going to go through here 20 times and sum all the outcomes. You take the piece of data minus the mean of the x's over the standard deviation of the x's, times it by the y piece of data minus the mean of the y's over the standard deviation of the y's. You'd multiply these two values together, and you'd get one value for the first ordered pair. Then you go back and you do it again for the second ordered pair, and you do it for all 20 ordered pairs. Add that up and then divide or multiply by this fraction. Now the calculator will do this computation for you, and I have never really seen a multiple choice question or a free response where they require you to calculate this by hand. So I don't think you need to worry about that. You do need to know how to interpret it. And here's the key thing, is it measures two things. It measures the strength and the direction of your data. It is always going to be a number, and it measures the strength of the linear relationship between two quantitative variables. So what does the strength and the direction actually means? Well, the strength of it is one of the key characteristics, and the strength is that it is between numbers -1 and 1. So yeah, it's within this range. Correlation can never be lower than -1, nor can it be higher than 1. If correlation is a +1, it's perfect positive linear correlation. If it's -1, it's perfect negative linear correlation. In between here is where it starts to weaken. So in between -1 and 1 is the number 0, which means if you get a 0 as a correlation, there is no linear correlation. So this is the strength that we see. And again, the direction comes from just the sign itself, if it's positive or negative. Now, one question is this: is correlation a resistant measure of strength? That is, can it resist an outlier? If we have an outlier in the data set, is it going to kind of ward itself off and not be impacted by that outlier? So how resistant is it? We'll investigate that in a little bit. So you are going to be asked to interpret R. So the key thing here is to always first look at the scatter plot. You want to see if there is somewhat of a linear relationship. So always plot your data first to see if, again, the linear form is there. For example, if it comes back that the R, or correlation, is 0.74, what does it mean? Well, 0.74 is pretty close to 1, so it's moderately strong. It is a positive because it's a positive value, and we're talking R, which means linear relationship. So in case of here, a 0.74 is a moderately strong positive linear relationship. Again, it talks about the direction, the form, and the strength. So DOFS is really covered in the R. So if you're asked to explain the R, it's really talking about DOFS. Now, we're not going to actually calculate the correlation for these 4 graphs. We're going to estimate what we think it is. We're going to think about a number between -1 and 1, and if it's positive or negative. In this first example here, we clearly see that there is a positive, fairly strong linear relationship. So I'm going to estimate that the R in this case is approximately a positive 0.9. Now, in order to be a positive 1, you would have to see every single point on the scatter plot land right on the line. Okay, let's look at this graph next. This one looks like it still does have somewhat of a positive relationship, but it's definitely not that strong. I'm going to estimate here about a positive 0.5. This graph here still looks like it might be going positive. It maybe could go negative. This is probably more of a positive one in that direction. Definitely not as strong, so I'm going to say a 0.3, maybe even a 0.2. This last graph here looks like it does kind of switch direction and it goes negative. So I would say that the correlation in this case is about a negative, and it's not strong, maybe a 0.2 or a 0.1. In this part of the example, they say to look at scatter plot B, which is right here. And this is the number of storms predicted and the storms that were observed. In 2005, 27 named storms included Hurricane Katrina. What effect would this have on the correlation if we remove it? So I think if we look at this point right here, this guy, and if we remove that, what impact is that going to have on our correlation? Recall before we said the correlation was about a positive 0.05. I would say that this point here was causing me to actually make the line to go up in here. If I remove this point, I'm not sure if the line should go here or should go here. It's not as clear cut. So on this one, it looks as though what would obviously happen is that the correlation here is going to go down. Now, I'm not sure if it's going to be positive or negative, but for sure going down is something we could say. Maybe it's going to be a positive 0.02 or a negative 0.1. All I know is it's going to be less linear. Let's look again at the sprint and long jump data that we had in previous examples. So here's our scatter plot, and they went in and calculated the correlation for us. It came back at a negative 0.75. They want us to explain what this value means. So really, this is where the DOFS comes into play, with exception to the outlier. We can tell from this correlation that it's negative for the direction. The form by the scatter plot is somewhat linear, and that the strength of it is somewhat strong. So what I'm going to say here is there is a strong negative linear association between sprint and long jumps. And that would be a nice way to conclude what we see is happening. Now, I think it's important to point out the AP common mistake, and it says here that the correlation that's near 1 does not mean the relationship is linear. You must start by looking at the scatter plot of the data to be sure that DOFS should be addressed accordingly. Be very careful if you have a free response question and they ask you this and you do not have a graph of the data, but you just have the ordered pairs. Plot the data first as a confirmation that you do see somewhat of a linear pattern. Now let's look at this. What effect would removing the student who is at 8.09 seconds and 151 feet have on the data? This is that particular student. Remember, the correlation before was a negative 0.75. If we remove this data point, it's still going to be negative, but it's going to be even stronger of a relationship. So what we could see, and I will tell you, I did remove this data point and I recalculated the correlation. The correlation this time came in at negative 0.88. So what we see is it's going to become closer to negative 1. Now, what effect would removing the student at 9.49 and 48 have on the correlation? That student is this one right here. So I'm going to highlight that individual student and talk about what effect I think that would have on the correlation. So before, the line was probably drawn somewhere in here because it was using this data to guide it. If that data is gone, it's probably going to look a little more flat and horizontal. So it's going to cause it to be less linear. Again, I will tell you, I recalculated the correlation and it came in at a negative 0.67. So what you see is it's going to move closer to 0. Now, the one thing to highlight about these two different possible outliers is you see this one here, this ordered pair, it's in the range of these X values, but it's a little bit higher up on the Y. Versus this guy here is kind of out on its own on the X values. And what they see is that outliers that are more because of the X values tend to be more influential on the data. So you may see the correlation get impacted more. Now, if you actually look at this one, though, if it was at negative 0.75, here it went kind of more linear by 0.13. Here, it actually didn't impact numerically as much, but what you're seeing is this is more influential and that it's going to make it less linear. A lot of the times you will see the actual correlation. If it was here, it's going to drop a bit more when the x's are pulled out more to the right or more over to the left on their own. Again, what we're seeing here is that the linearity of this was more impacted because of the extreme outliers in the x direction. In our scoring essay example, Peter and Elaine are both English teachers at the high school. Students think Elaine's a harder grader, so Elaine and Peter decide to grade the same 10 essays and see how their scores compare. The correlation is 0.98. So here we have Peter's scores, and here we have Elaine's scores, and it is the averages of the tests that we're going to see graded. Is it true, based on this graph, that we can conclude Elaine is a slightly harder teacher? Well, if you look at this, the perfect correlation, such that the slope is 1, is right here. So this is a perfect correlation. And we're going to see the grades are pulled more a little bit towards Peter's. So yes, we could say Peter is an easier scorer based on what we see in the scatter plot. To wrap this up, there's a few facts and causations about correlation you want to really keep in mind. First thing is that correlation makes no distinction between the explanatory and response variable. And what that means is, remember when we had to make our scatter plot and we chose what was explanatory and response, it doesn't matter which goes which. The correlation will not be impacted if we reverse the order of our scatter plot. Second point, because R uses the standardized values of the observations, R does not change when we change the units. So if we were going to label this with inches versus feet, it's not going to change the R. So we would have to scale the data. If we go from inches into feet, we divide by 12 inches, or we may multiply to go the other direction. The R will not change because of that. Correlation itself has no unit of measure. We don't say that the R value is in, inches or feet or what have you. It's just R. 4, correlation requires that both variables must be quantitative. Again, we can only do this with scatter plots, so we have to have 2 sets of quantitative data. 5, correlation measures the strength of only the linear relationship. This shows nothing about a curved or parabolic pattern. Correlation does not describe any other relationship between variables, no matter how strong it is. R is just for lines. Point 6, like the mean and standard deviation, correlation is not resistant. We saw, especially when we had an outlier towards the x-axis, it was strongly affected by the outliers. So correlation cannot ward off outliers. It is not resistant to outliers. It is impacted by it. And lastly, correlation is not a complete summary of the 2 variable data, even when the relationship between the variable is linear. We do want to address some more components about that we'll talk about later.